So how big is 3C273? Note that the X-ray image of the round object is much smaller than that of Cas, but of course that could be because of the stupendous distance to the quasar. In fact, the size of the object is consistent with a point source of light, such as you might see when you look at an ordinary star that resides in our galaxy. However, we can certainly see the jet emanating from the side of the quasar and measure its length. So how big is the jet of 3C273? We've zoomed in here, and we are now going to keep an eye on our magnifying box here as we look at this jet in detail. We have to find out how many pixels represent the length of the jet. Be careful, the jet is at almost a 45-degree angle, and just counting pixels will result in an error. Remember that each pixel along a side spans half an arcsecond, so along the diagonal, the angle spanned is 1.4 times that. It might be helpful to rotate the image so the jet is horizontal. You can do that by going to Edit, change our pointer to Rotate, and now you see our cursor has changed to a rotate symbol. Click on the image and rotate. This is fun. Now we can get the jet to be almost horizontal, and after we go back to a pointer, we can set the pointer near the jet itself and start scrolling over using our right and left arrows and just count the number of pixels in the magnifier box that corresponds to the length of the jet of 3C273, and thereby get a good estimate for its extent. Let's do the calculation at the blackboard. Along the diagonal, the jet is about 15 pixels long, so the angular extent in the sky has to be about 15 pixels times 0.5 arcseconds per pixel, which is the element of resolution for the Chandra satellite, times 1.4, because we're seeing those pixels, kind of like as a diamond shape here, and we're measuring the distance across the diagonal instead of along the side. And this works out to about 10 arcseconds. So the jet itself is 10 arcseconds in angular extent. Therefore, we can figure out what the length of the jet is. It's just going to be 10 arcseconds divided by our handy-dandy number 206.265 arcseconds per radian times our distance to 3C273, or about 700 megaparsecs. Thus, the length of the jet in space emerging from 3C273, our little dot up here, is about 35,000 parsecs. This is bigger than the entire size of our Milky Way galaxy. In fact, recent observations using the Chandra satellite have shown a faint connection between the jet and the central part of the quasar, so the jet is about twice this size. By now, you're probably wondering, the main part of the quasar looks like a ball about 20 pixels across. Doesn't that represent the size of 3C273? The answer is no. The reason is very similar to what happens when you take a photograph of a very bright light. The picture kind of spills over into adjacent regions on the film or adjacent pixels on the digital detector. Since the jet is much fainter, it really does represent more accurately a true size. In astronomical lingo, we say that the jet is resolved because we can see details over its many pixels. But the main quasar is unresolved, since it is a featureless blob consistent with a point-like object that is very bright. It is exactly the same situation we have with stars in optical telescopes. All the stars, other than the sun, are so far away as to be point-like in a telescope, although the brighter ones will appear to be bigger blobs on a picture because of the spillover effect. So we need another way to measure the size of the quasar. The answer comes from an unexpected place: the quasar's time variations. To see how this helps us, imagine a soccer field with you standing a few blocks away on the outside. When a team scores a goal, a roar goes up from the crowd. All at once, everybody is screaming. But you don't hear the loudness immediately. The sound from the part of the stadium nearest you arrives first, followed by the sounds from the more distant parts. It takes time for the sound to build up. In fact, if the velocity of sound is given as c, the amount of time it takes is the length of the stadium divided by the velocity. Okay, here's the size of the stadium, and if all of the stuff, in this case sound, is traveling at speed c, it will take a time t for that sound to build up. Light is exactly analogous. Here is a schematic of how an object of radius equal to 1 light week might appear. Light from the side closest to the Earth will arrive about 2 weeks earlier than the light from the point furthest away. So the light curve would appear to ramp up over a period of several weeks, even if the object changed its output all at once. Thus, by measuring how long it takes for the light coming from the quasars to change in intensity, gives us an idea of how large the central engine is that is responsible for emitting the radiation. Typical optical variations are shown here for the quasar 3C279. These variations in 3C279 were discovered from a study of the Harvard survey plates, which are optical photographs by Lola Ikas and Bill Liller, and established time variability on the order of months. Since then, some quasars have exhibited variations on a scale of even minutes. Thus, the size of the central engine of these objects must be incredibly small considering their stupendous output. If L equals c times t, where now the c represents the velocity of light, we have objects that must be no larger than our solar system in size, and yet their output is hundreds of times that of an entire galaxy.